Hey everyone, and welcome to This Explainer. Have you ever just stared at a carton of milk, or maybe a can of soup, or even a bag of decaf coffee, and wondered exactly how they're made to be so perfect? I mean, we usually just think of heat as the main tool in food science, right? Cooking, baking, boiling. But there's actually this hidden superpower at work, a totally invisible force that's transforming the foods we consume every single day. Today we're going to explore the absolutely incredible world of high-pressure processing.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the invisible processing force, move into homogenization, then controlling pressure, cold pressure, and finally wrap up with the future under pressure.
Section 1. The invisible processing force, a hidden superpower.
So I want to pose a bit of a micro-mystery to you. How do you actually sterilize a really delicate liquid or, say, extract caffeine from a coffee bean without just completely cooking away its natural flavor? Traditionally, we boil things, but let's be real. Heat can be incredibly destructive. It shrinks foods, it degrades those essential vitamins, messes with the texture, and totally changes that fresh taste. So we need a delicate balance, right? A way to preserve all that quality without relying entirely on boiling heat.
And that brings us right to our core definition. In food processing, high pressure is basically the application of intense physical force. Honestly, it's kind of the holy grail for food scientists. By manipulating pressure, we can actually alter a food's physical structure, safely preserve its quality, and even selectively extract specific components, all while completely bypassing the damage caused by heavy thermal degradation.
Section 2. Homogenization. Smoothing milk out.
Think about the milk sitting in your fridge right now. Why doesn't all the fat just float to the top and form a thick layer of cream? In raw milk, it naturally separates. That's just what it does. And this was actually a massive mechanical problem that early dairy technologists had to solve just to create the smooth, uniform market milk that we all drink today.
Well, the solution lies in this massive, literally crushing number, 2,000 to 2,500 pounds per square inch. To stop that separation, dairy processors use these heavy-duty positive displacement pumps to force fluid milk under this immense heavy pressure through an impossibly tiny hole, an orifice, inside a machine called a homogenizer.
Now, what's really interesting about this slide is seeing it mapped out. If you look under the pressure heading in these academic source notes, you can see that homogenization can happen in a single stage right at that 2,000 to 2,500 psi mark, or it can actually be split into a double stage. That's where they hit it with 2,000 psi first, followed by a secondary stage of 500 psi.
So what's the actual results of all this crazy force? Well, in raw milk, those fat globules vary wildly, anywhere from 1 to 20 microns in diameter. But as they get shoved through that tiny orifice under massive pressure, the physical shearing force literally shatters them, just breaks them apart into minute particles under 2 microns in diameter. And at that microscopic size, they stay perfectly evenly distributed throughout the water phase of the milk. Pretty cool, right? Moving on to Section 3, Controlling Pressure, the retort.
Okay, so to commercially sterilized canned foods, you've got to get them way hotter than just boiling water. To hit a target temperature 127 degrees Celsius, processors have to use steam pressures of approximately 20 psi above normal atmospheric pressure. But here's the catch. Adding that much heat creates a really dangerous physical reaction inside the actual container.
It kicks off a literal battle of pressures. On the inside, the moisture of the food starts to boil and turn to steam, which creates this massive internal pressure expanding outward. If left unbalanced, the cans would just burst wide open, literally explode. So to prevent that kind of mechanical damage, processors have to meticulously control the external pressure. They use steam, overriding air, or hydrostatic force applied to the outside of the container to hold the whole thing perfectly intact.
Take a look at these massive industrial chambers. They're called retorts, and this is where those high-stakes pressure battles actually happen. These are heavy-duty, pressure-tight batch vessels built with special locks. They safely admit the cans, apply that high-pressure sterilizing steam, and very carefully balance that internal container expansion we just talked about.
Now, for continuous, non-stop canning, the industry uses machinery like the hydrostatic cooker. And honestly, what is absolutely mind-boggling about this system is how it controls pressure. As the cans travel through it, their internal boiling pressure is balanced by nothing but water. Specifically, towering 14 meters, that's a 46-foot high column of hot and cold water. The sheer hydrostatic weight of that water column perfectly counteracts the intense pressure inside the cans. It's brilliant.
Section 4. Cold pressure. Inactivating microbes.
This is where things get really cutting edge. We call this high hydrostatic pressure, or HPP for short. Instead of using steam, liquid foods, or foods with suspended particles, are subjected to several thousand atmospheres of pressure. Several thousand! It is a staggering amount of force. And it's basically the ultimate solution for inactivating microorganisms and enzymic activity entirely, completely bypassing the destructive nature of heat.
Let's move to and see how this builds step by step. First, the food is sealed inside flexible pouches. Next, those pouches get loaded into these heavy-duty pressure vessels. Then, water is pumped in to completely fill the space, and all the air is sucked out. Finally, boom, the system applies massive hydrostatic pressure directly through the water itself. And because that pressure is transmitted uniformly by the water, the food is perfectly preserved without a single degree of added heat. It's like magic, but it's just physics.
Section 5. The future under pressure.
A perfect, almost sci-fi example of this modern application is supercritical fluid extraction. This advanced process takes everyday carbon dioxide and forces it under high pressure and reduced temperature into a supercritical state. In this highly pressurized state, it actually becomes a safe, completely non-toxic alternative to chemical solvents. It's perfect for selectively extracting really delicate flavor compounds from spices or safely pulling the caffeine out of coffee beans.
And this brilliantly illustrates exactly why it works so well. By keeping the pressure super high, the carbon dioxide actually behaves with the solvent power of a liquid. That's what allows it to dissolve the caffeine. But simultaneously, because of the reduced temperature, it retains the penetrating ability of a gas. So it just slips right into the coffee bean, does its job, and leaves absolutely zero toxic residue behind.
So what does this all mean for us? I want to leave you with this final, provocative thought. We've seen how high-pressure processing can shatter fat for perfectly smooth milk, balance the boiling fury inside a tin can, extract delicate flavors, and completely inactivate microbes without a single spark of heat. If pressure can perfectly preserve our food while maintaining all its natural flavor and texture, are we literally witnessing the end of the traditional oven and stove in industrial food science? It is a truly fascinating future to consider. Thanks so much for joining me on this explainer, and remember, always keep questioning how your food is made. Catch you next time.